This is our last section in 11.4, another quick unit for us. Our objective today is to be able to relate scale factor, length, area, and volume. So kind of bringing this all to a close. So let's go ahead and look at warm-up number 1. And as I've suggested the last couple of sections, maybe you want to pause and try this first by yourself. This is another really good problem. It says the shape of a large storage container is a cylinder with half sphere on top. So we can see our picture, we see our cylinder, we see that half sphere on top. What is the volume in cubic meters of the container? So I know to be able to find volume of anything with a circular base, I need to know a radius. So the first thing I'm noticing is what they've labeled on the bottom. This is 18 across, which means that we have a radius, which is 9. Which means we should have the same radius up here with our half sphere. So this problem can be a little tricky if you're not really thinking about this close, because we know in order to find the volume of the whole shape, we'd have to take the volume of the cylinder, so kind of that bottom portion, and we'd have to add to that the volume of the half sphere. Well, I can find the volume of a sphere pretty easy by taking pi times that radius times the height. Now here's where the interesting part comes in. Notice your height is 40, but the height spans the whole height of that whole object, that whole storage container. So now you have to figure out what is the height of just a cylinder, what is the height of just a sphere. So maybe after a little bit of thinking, you realize, well, I know that the radii are the same in every circle and every sphere. So if I'm thinking about this top piece right, there's also a radii that would represent the height, which could be translated over here to realize that this piece is also just 9, which means the rest of the height would have to be 40 minus 9, so 31. So I can complete my cylinder volume portion there with 31. So kind of an interesting problem. So if you got that, good job. Plus half of our sphere. So I'm going to go ahead and think about my formula with the 2/3 pi times the radius squared. So we're looking for the volume, so we should be able to plug all of this into our calculator the way we've got it written out. So I'm going to take my pi times my radius squared times 31. But I need to add to that 2/3 times pi times that radius squared. Oh, I just realized I messed up. On my sphere, it should have been a cube, that half sphere. Let me go grab that again. And let's change that to 9 cubed. I realized I wrote that wrong. I'll have to change that. So cubed. Oh yeah, that's going to change it just a little bit. So 9,415.35. Let me change that to a cube really quick. Let's see, so 9,415.35, and we are in meters cubed. So kind of a fun problem putting things together like that. All right, the last thing we're going to work on in this unit relates us to some scale factors. So let's go ahead and look at some shapes. It says below that the drawings are dilations of one another, and the length and the area is what we're going to be comparing. So we can see this is labeled. We have our original drawing, we have our dilated drawing. So definitely we know dilation either gets larger or smaller. So we've got a triangle that's gotten bigger, and we have a circle that's gotten smaller. So let's start with length scale factor. So if we want to find length scale factor, we have to take the dilated length and compare it to the original length. And we're going to call this ratio K. So my dilated shape is clearly bigger, so my lengths are going to be bigger than my original length. Now we do want to we want to use corresponding parts of this. So in this case, both sides of my triangle are 6 and both sides are 3, so that would make it a little bit easier. But maybe I think about that vertical side being compared to this vertical side, the horizontal to the horizontal, etc., if they weren't the same numbers. So I'm thinking to find my scale factor, to find that K, I would need to take my dilated length compared to my original. And of course, I will always simplify, which this makes sense. To go from my original to my new, I have to times by 2. Let's look at our other ratio, area scale factors here. We could take the ratio of the dilated area to the original area. So I've already calculated these, so we don't have to do that too, but the area of our smaller triangle is about 4.5 centimeters squared, and the area of our bigger is 18 centimeters squared. So if I want to make a scale factor, I'm going to take my my dilated area, so this would be called K squared, is going to be 18 compared to the 4.5 from my original. Now, just because this is with decimal, maybe we want to grab our calculator really quick and take that 18 and divide it by 4.5, which gives us a 4. Now, one thing I do want to point out is we're finding K and K squared, so there should be a relationship between these. And I do notice that if I take 2 and square it, I do get that 4. So we're seeing that relationship for K and K squared. If I want to know the relationship for area and I know the relationship for length, I can just square that. So we should see a similar thing happen with triangles. If we look at the length of circles, and in this case, we're really just looking at a radius. So to find our scale factor here, we're going to take our dilated, which this time is smaller, as compared to our original 6. So this time we're saying that this triangle or this circle, if we multiply by 1/3, we would get 2. So this radius of 2 circle is 1/3 the size of its original. So we should see kind of a similar pattern as we saw above. Now, if we think about this, above we saw 2, which ended up to be 2 squared. And now we have 1/3, so our area should end up to be 1/3 squared if we're doing this correctly. So again, I've got this calculated below, and I left it in terms of pi just so that we don't lose any decimals and we can see this relationship better. But if I take the area of my dilated circle, so 4 pi, compare it to my original 36 pi, those pi's will divide out, and 4 over 36 is 1/9. So just like we saw above, we could think of this as 1 over 3, but that whole amount would need to be squared, which 1 squared is 1 and 3 squared is 9. So we see that relationship between our scale factors of 1/3 and 1/3 squared. So right below this, it says, note, if a figure is dilated by a scale factor of K, its area is K squared times the area of the original figure. So there's this relationship. So let's go back up here for a second and let's look at our triangle. It says the area is K squared times the original figure. Well, my K squared was 2 squared times the original area, which was 4.5. is supposed to be the area of the dilated shape. So we know the dilated area was 18. So 2 squared, which I know is 4, times 4.5 does give me 18. So that's kind of an interesting thing right there, using those scale factors. Let's try it again with the circle. So if we want to find the area of the dilated shape, if we take the scale factor for K squared, which would be 1/3 squared, times the area of the original, so 36 pi, we are supposed to get the dilated shape area 4 pi. So notice we want to keep it in terms of pi, so I remember that this is really 1/9, and 9 can simplify with 36 4 times, so that's going to end up to be 4 pi. So there it happened for us again. If we found these ratios and we want to find area, we could just multiply the area of the original by that scale factor for that dilation. So kind of a cool idea. Let's look at the next page. All right, in this side, we see a similar setup that we saw on the front side. We see our original, and we see our dilated, and we've got these two columns. So above it, it says the three-dimensional figures below are dilations of each other, or one another. The length and volume of each scale factor, each factors of each figure are compared. So let's do a similar thing we did on the front side, and let's start with the length of our dilated and our original length. So again, it doesn't matter which length I choose, I just wanted to make sure I have corresponding lengths. So if I take from my dilated the length 6, I just want to make sure it corresponds, in this case, to 3. So my scale factor is 2. Now I want to do the same thing for volumes, and you'll notice maybe I've got this typo, so you're going to change this really quick if your copy says the same thing. This is supposed to say volume instead of area. So change those areas to volumes if yours doesn't say that already. So find our relationship for volume ends up to be a k cubed, because we know volume is in cubed units. So I'm going to take the volume of my dilated, so 60, as compared to the volume of my original, so 7.5. So when I take those relationships and I divide them, 60 divided by 7.5. So I realize that that's going to be 8. And I recognize that 2 cubed is the same thing as 8. So there's my scale factor cubed, gives me that relationship for my volume. Let's do a similar thing with our cylinder. We are starting with a cylinder that's larger and we're dilating it to something smaller. So I won't be shocked if my ratio is a fraction. I could use my radii or my height. I'm going to go ahead and use my height from my dilated and the height from my original. So there's that fraction that I was thinking I'd get. And a similar thing will happen with my cubed. If I take the volume of my dilated, so 12 pi, as compared to the volume of my original, 768 pi, the pi's will divide out, and I'm going to take that fraction and see if that will simplify. So we're going to end up with 12 over 768, which is a 1 over 64. And when I cube a 4, I do get a 64. So there's my ratio cubed. So right below that, it says to note, if a figure is dilated by a scale factor of k, its volume is k cubed times the volume of the original figure. So similar to what we saw with area on the front. If I want to find the volume of a dilated shape, as long as I know the scale factor, I can cube it and multiply that to the the volume of my original shape. So in this case, 7.5. So 2 cubed, and I'd like to multiply that to 7.5. So my new dilated area should be 60 feet squared, and that's exactly what's already been figured out. So that's kind of cool. Let's try it again on the cylinders. So if I want to find the cylinder of a dilated shape, I just need to know its scale factor. So 1/4 in this case, and I would cube it because it's volume, times the volume of the original. So 768 pi. So I know 4 cubed is 64, and 64 divides into 768. Let's see, 768 divided by 64 is 12, which is exactly what I wanted it to be because I knew my volume dilated there was 12 pi. So if we know our scale factors and we have an area or a volume, we can find area or volume of dilated shape. So that's kind of cool relationship there. Let's look at a couple examples where we want to find some scale factors. So example 1, if the original cylinder has a radius 4 inches and a height of 10 inches, how will the volume compare to a cylinder with a radius, with the same radius, but double the height? So let's go ahead and do some calculations. Let's find the volume of that original. So it says it has a radius of 4 and a height of 10. So pi times radius squared times that height. So that's going to find the area of that cylinder. So I'm just going to think of this in terms of pi for right now. I think that'll be a little bit easier for me to see than decimals. So I know 4 squared is 16, and 16 times 10 would be 160, and then we have our pi. Well, the volume of a new cylinder where the radius stayed the same but the height has doubled. So pi times the same radius, but my height has now doubled. Okay, so I'm going to see the volume here. So 16 times 20, maybe I'll grab a calculator just to make sure on that one. That's going to be 320. So how will the volume compare to a cylinder with the same radius, but we've doubled the height? So we've kind of looked a little bit at stuff like this. If I want to find a scale factor, how much has it really changed? Then I need to take that original and I'm going to compare it to that doubled height, because that's going to tell me how much it's changed. So in this case, my original volume was at 160 as compared to that doubled height volume, which was 320 pi. So our pi's will divide out, and 160 is half of 120. So our original shape is half the size of our new shape if we've just doubled the height. So when we double the height, then it changes that by 2. We're half of the original or double. Let's go ahead and look at example 2. If the original cylinder has a radius of 4 inches and a height of 10 inches, how will the volume compare to a cylinder with the same height but double the radius? So similar idea, we're looking at that old, which is still pi times the radius squared times that height, so still 160 pi. But our new one says, what if we just double the radius? Well, doubling 4 would make that radius of 8, and we're keeping the same height. So into my calculator, I'm thinking 64, I guess I didn't need a calculator, 64 times 10 would be 640. So to make our scale factor, we're going to take that original, which was 160, and compare to our new. So again, those pi's will divide out, and we're thinking how many times does 160 divide into 640? So it's going to divide in there 4 times. So we end up with a scale factor of 1/4. So when we change the radius and double that, then we end up with 1/4 the size. So our radius being doubled and our height staying the same, it tells me that my original shape is 1/4 the size as our new shape. So go ahead and self-assess, and good luck on your assignment.